Welcome everybody. In this video we are going to talk about block diagram as a part of chapter 3, which also include signal flow graph and Mason's rule. For individual subsystems, usually it's represented by a single block with the input signal, output signal, and transfer function, which relate between the output and input. So GS is equal to CS over RS. However, most of the existing control systems are more complicated and consist of multiple subsystems, not only single subsystem. Since we have multiple subsystems, that means we have multiple transfer function and multiple blocks, similar to the single block. In order to represent such complicated system, we have two methods. One using block diagram and the other using signal flow graph. In order to simplify such complicated control system, we need to perform reduction techniques in case of the block diagram, or we need to use Mason's rule in case of the signal flow graphs. After we simplify the control system or the complicated control system, we can perform further analysis to find or to study the transient response, steady state response, and also find the stability of the system. So our task in this chapter will be how to simplify the complicated control system into a single transfer function. After that, this single transfer function will be used for analyze the performance of the control system. For the complicated control system, which consists of multiple subsystems, we have extra elements in the block diagram, which are summing junction and backup points. So these two extra elements, in addition to the three main elements that we already mentioned, which is the input, output, and transfer function, will be used to connect subsystem with each other. So as we can see here, these are this is the main or the single block control system, which has three elements only: input, output, and transfer function. And here we have the extra element, which is the summing junction and backup points. So we can see here the summing junction. This we call it summing junction here. And this summing junction has multiple inputs and convert it into one output. So we have R1, R2, R3, three inputs here in this case. And the output will be represent the algebraic sum of these three inputs. So we have R1 positive, R2 is positive, R3 is negative. So R1 plus R2 minus R3. In the case of the backup points, we have one input here, which is RS, and it's distributed into three inputs: RS, RS, RS. Each one input will go to one subsystem. So we call it backup point. For the topology of the block diagram, we have three types of topologies. And this topology we need to understand because we are going to use this topology to simplify the complicated control system. So the first topology, we call it cascade form. The second is parallel form. The third is feedback form. We are going to see each type of the topology and how this topology will be used to simplify the complicated control system. This is the first one, which is cascade form. And the cascade form here, it means we have multiple subsystems which is connect in series, so in cascade. So the first transfer function here for the first subsystem, the second for the second subsystem, the third is for the third subsystem. So we have three transfer function, and the output of the first transfer function represent the input for the second, and the output of the second represent the input for the third, and so on. So in order to find to simplify this cascade form of control system, the equivalent transfer function of this system represent the multiplication of the three transfer functions. So we have G1 times G2 times J3. or G3 times J2 times J1, it's the same. And we have the input, which is the input at the point R1 or the point G1, which is R1, RS, and the output is the value of CS. So this system, which consists of three transfer functions, is simplified into these single blocks, which consist of one transfer function only, which is J3, J2, and J1. So this is for the cascade form. In the future, if you have any type of cascade form in your complicated system, you need to merge these subsystems into one single block or one single transfer function. This is the second form of the or second topology, which is we call it parallel form. And in the parallel form here, as you can see, we have one input, for example, and this input is distributed into the three subsystems. So RS will multiply by J1 to give you X1, RS will be multiplied by J2 to give you X2, RS will be multiplied by J3 to give you X3, and you can see here X1, X2, X3 what represent RSG1, RSG2, RSG3. These the three the three subsystem are connected in parallel. So the input is connected to the input, the output is connected through this summing junction. So as we can see here, the output value, which is CS, is equal to the algebraic sum of the three inputs or the three subsystem transfer function, which is J1, J2, J3 multiplies by the input signal, which is RS for all subsystems. In order to find the equivalent transfer function for this subsystem, J equivalent equal to plus minus J1 plus minus J2 plus minus J3, and this J1, J2, J3, the signal here or the sign of J1 and J2 and J3, it depends on what is the value here at the summing junction. If it's positive, so it's keep positive. If it's negative, it become negative. The third topology here, which we already see in chapter 1 when we talk about the closed loop transfer function or feedback transfer, closed loop control system or feedback control system. And in this, we call it the feedback form. As we can see from this symbol system, which consists of two subsystems here in this part, after the summing junction, we have two subsystems, J2 and J3. And these two are cascade because they are connected in series. And we have feedback go through H1 and H2, but H1 and H2 also are cascade here in this case. And we have the output here. And the whole system, the whole of this system, which is consists of J2, J3, H2, H1, is connected in cascade with the first transfer function, which is J1. Actually, since we have this value or this feedback come from the output of our system and go again to the input of our system, so we call it feedback form or feedback topology. This is the symbol form of feedback topology, which consists of input, summing junction, transfer function, output, and from the output we have the feedback go through HS again to the summing junction here. So in order to simplify such feedback form or feedback topology of control system, we have this will be represent the equivalent transfer function for our system. So G equivalent equal to GS over 1 plus minus JS HS. Plus minus value here, this is the plus minus value. It depends on what is the value here, positive or negative. Is it positive feedback? So this value would become, or this sign become positive, or negative feedback, so this sign become negative. So in the case of the negative feedback, you can see here, the top is positive, the top is negative. The bottom is negative, the bottom is positive here. So it will be reverse. So if you have a negative feedback, it becomes GS over 1 plus GS HS. If you have a positive feedback, it becomes GS over 1 minus GS HS. Actually, the derivative for this transfer function or for this equivalent transfer function for the negative feedback system is explained here in this slide. So you can see here, you can see the feedback or the negative feedback control system, block diagram control system, is represented here with the transfer function and the feedback function here. And also we have the summing junction and the output and the input signal. So this is the input is go here. And usually the signal which is ES here represent the error signal. The error signal come from the input value minus the feedback value. So as we can see here, ES can be represented by the equation here, equation number 1. ES is equal to RS, which is positive here, RS minus CSHS. So RS minus CHSS. But if I ask you now, what is the value of CS actually? CS is come from ES times GS. Because if ES go through this transfer function, it will give you the value of CS. So CS is equal to ES times GS. By substitute the value of or the value of equation 1 into equation 2, that means I will replace ES here by the value of ES in the equation number 1. So it becomes CS is equal to RS times GS, RS times GS, and CSHS times GS. So we got this equation number 3. To simplify this equation, we transfer this value of CSHSGS to the left side of the equation number 3. So we got CS plus CSHSGS equal to RSGS, which is this one stay in the right side. Now we will take CS as a common here, and we have 1 plus HSGS, which equal to RSGS. This will give you CS over RS equal to GS over 1 plus GS. CS over RS, that means we divide this one CS over RS on the left side. On the right side, we have GS, and we divide by 1 plus GSHS. So this form here, or this transfer function, or this equivalent transfer function, which equal GS over 1 plus GSHS, is the same that we show in the previous slide, which is the GS equal to GS over 1 plus GSHS. So this is how we can simplify or find the equivalent transfer function for such feedback system. Usually, the transfer function or the equivalent transfer function of feedback system is equal to transfer function or the open loop transfer function, which is GS over 1 plus GSHS, whatever is the value of GS, or even we have multiple transfer function G1, G2, G3, H1, H2, H3, we still find this one is the forward transfer function and this one is the feedback transfer function. So this will be the equivalent transfer function for our feedback. Actually, these three form of or three topologies and their simplification, we are going to use them in our reduction technique to simplify the complicated control system. In order to simplify complicated block diagram of control system that consists of multiple subsystems, we need to use reduction techniques. So in this table, we will see some of reduction techniques. First is combining block in cascade. So if you have multiple blocks connected in cascade like G1, G2, their equivalent diagram will be a single block with a single transfer function, which equivalent to the transfer function of these two transfer function of subsystems. So the transfer function here is G1, G2 or G2, G1. It is the same. So it is the multiplication of the both transfer function. If you have three block diagram in cascade, also the equivalent will be multiplication of the three transfer function of the three subsystems. The second technique is moving summing point. So we learned that we have some summing point and pickup point, or summing junction and pickup point. So sometimes this summing point exists in some place which make it complicated to simplify the control system. So we have to move it from its place to another place in order to simplify the control system. So in this case here, we will move the summing junction from the input of the system to the output side. So as you can see here, this is the original block diagram, and here is the equivalent block diagram after we move the summing junction from here, from this point at the input into the output. Actually, what we need to consider during the moving of pickup point or summing junction, we need to consider what will be the value of the output. So the output of both systems should be the same. X3 on the original in the original system here must equal to X3 on the modified or the equivalent system. So in the first case here, X3 is equal to the summation of X1 plus minus x2 both are multiplied by j. So it's become jx1 plus minus jx2. In the modified one or in the equivalent block diagram here, also the same. We need to multiply x2 here by j because we have x2 go through j. So in this case also we have same x2 times j, and here we have x1 times j. So the value of x3 in this case become x1 times j plus minus x2 times j. So it is the same as the original x3 here. So this x3 is equal to that x3. The third technique here, the third technique in this case, moving a backup point. So same like we did here, we move the summing junction. Here we move the backup point ahead of a block. That means the original place or the original location of the backup point is after the block of J here, and in the modified system it's become before. So we move from this point to ahead here. So as we can see, we should also consider that the value of the x2 in the original system is same as the value of x2 in the modified system. So what is x2 here? x2 is equal to x1 times j. But when we move this summing backup point to the input here, x2 be still the same, x1 times j, and this the other x2 that we have also should be multiplied by j. It's become also x1 times j. So x2 always equal to x1 times j. So the value here or the equivalent diagram give you the same output as the original diagram. The third technique here or the fourth technique here that we have, we need to move the backup point from the input to the output. In the previous one, we move it from the output to the input. Here we are going to move the backup point from the input to the output. So the value of at this point here we have x1 okay, go to through the transfer function, it gives you x2, but also the same x1 we take it to be input for other subsystem. So if we want to move this point from before j to behind j here, x1 will go through j to give you x2, so nothing change here. X1 go through j give you x2, but if I want to take another input for x1, I need to modify or to divide this value over j. So I have x1 times j divided by j. So j will go with j and the output still x1, same like that output. So this x1 same like that x1, that x2 same like that x2. Even we modify, even we move the backup point from the input to the output, but still keep the same values. Next, moving summing point ahead of a block. So in the second case, we have summing junction in the input, we move it to the output. Here we have the opposite, we have summing junction at the output, we need to move it to the input. So in this original system, the summing junction at the output, and here it's become at the input of our system or ahead of the value of j. So in order to move it to there, also we need to consider the value of j. So we need to divide x2 here over j. So the value that to keep the value of the output x3 is the same in both cases. So in the first case here, in the first case, the value of x3 is equal to x1 times j plus minus x2. x1 times j plus minus x2. In this case, the value of x3 is x1 times j plus minus x2 over j times j, so it's become also x2. So it will give you the same x2 value here. When I divided x2 here, divided by j, multiply by j, it's like I multiply x2 times 1. So it gives you the same value, which is x2 at the output, same as the original one. The last technique here, eliminating a feedback loop. So this we already mentioned before when we talk about the feedback topology, and we said if you have such feedback, either positive feedback or negative feedback, you need to simplify. You just need to use the general formula of equivalent transfer function of the feedback system. So in this case here, we have the feedback is j, the transfer function for forward is j, for backward is h. So the equivalent transfer function will be j over 1 plus minus jh. So if it is negative feedback, it's become 1 plus jh. If it is positive feedback, it's become 1 over or j over 1 minus jh. So the value here plus minus, it depends on our system. Is it positive feedback or negative feedback? In order to understand these reduction techniques or to apply this reduction technique to simplify block diagram, we have some examples here. So in the first example here, it show you this is this system which consists of multiple subsystem G1, G2, G3, and some feedback H1, H2, H3. So we need to simplify the system to become a single block with a single transfer function. Here we have three transfer function and we have three feedback h1, h2, h3. We want to combine all these transfer function into a single equivalent transfer function and combine all these blocks into single block. So what we need to do here, we have to follow the reduction technique that mentioned in the table before. So in the case we can combine the blocks directly, so we can combine. If we cannot combine some blocks, we need to consider the moving of pickup point or summing junction. So in this figure here, the first thing that we have these two blocks are connected in cascade. So these two blocks here, G1, G2 and G3 are connected in cascade. So I can combine them into a single block, which is G2, J3. Okay, the next thing that we have here, we have three summing junction are connected in series here. So I can combine these three summing junction into a single summing junction with three input and single output. Sorry, with four input and single output. So we have here this one input, this is the second input, this is the third input, and this is the original input. So we have four inputs for summing junction, and we have one output which is at this point. So the three summing junction can be replaced by a single summing junction. We need to consider when combining these summing junction, consider the value or the sign of this input. So this is negative, this one is positive, so this is negative. So if it's negative, that means negative feedback. If it's positive, so it's positive feedback. After we combine these three summing junction, we can also combine these three feedback H1, H2, H3, because these three are represent a parallel form of the control system topology. So since their input is the same, their input is come from the same point, their output is go to the same summing junction. So these three systems are represent the parallel form. So here we have parallel form, here we have cascade form, here we can combine the three summing junction. After we do this simplification, the last step we need to combine, we need to consider this the total or the overall feedback system, then it will be in cascade with the J1. We can see here are the drawing or the steps to simplify the block diagram. The first, we combine three summing junction into one summing junction with considering the value or the value of the sign of the inputs. Here we have negative for H1, positive for H2, negative for H3. Then the next step, these two blocks are in cascade, so it give you J3, J2. Now H1, H2, H3 are in parallel, so it will give you H1, negative H2, positive H3, and with one input here. Since we already combined them in parallel, so we need to do algebraic sum for the all inputs, and we consider the sign. So here the sign, you can see here negative for H1, still the same, negative for H1, and negative times negative, so it's become positive for H2, and negative times positive, so it's still negative for H3. So we can see here how we simplify these three or these three feedback into a single feedback, which is because they are connected in parallel. Now the next step or the final step will be to find the feedback of this system. So this system will be, or these two blocks represent a feedback form of block diagram. So since they are feedback, we need to apply the general formula for the feedback system. Since this is negative feedback, we already say before, if it's negative feedback, so the equivalent transfer function will equal to gs over 1 plus gs hs. But in this case, gs is equal to j3 j2 and hs is equal to h1 minus h2 plus h3. So this feedback system can be simplified into a single block, which is represent gs over 1 plus gs hs, or if we substitute for the value of gs, it will be j3 j2 over 1 plus j3 j2 times h1 minus h2 plus h3. So this will be the value for this block, and this block will be in series with the second or the first block, which is j1. So j1 will be in series with this one, so we are going to multiply j1 times j3 j2 over 1 plus j2 j3 times h1 minus h2 plus h3. Now this system which consists, this system which consists of multiple blocks, 1 2 3 forward and 1 2 3 backward and 1 2 3 summing junction, is simplified into this single block with one transfer function, one input, and one output. So by using this block, by using this block, it's easy to simplify or easy to analyze the control system or the transfer function of this control system, so we can know if this control system is stable or not, if this control system, what is the value of transient response, what is the value of steady state response, and so on. I hope it's clear how to simplify this block diagram or this complicated block diagram. Here we have another example also. So in this example, we are going also to see how we can simplify this block diagram by using the reduction technique into a single block with a single transfer function. So in this example here, also we are going to simplify the values or the complicated block diagram into a single blocks. So before we go to do some moving for some junction or pickup point, we need to check, is there any cascade form, any parallel form, any feedback form can be directly applied to the system without moving. So we can see here, we can check, is G2 and G3 are in cascade? No, because we have here pickup point, so we cannot say J2 is in cascade with J3. Okay, is G1 and J2 are cascade? Also no, because we have a summing junction here between these two blocks. Is G1 with H1 represent a feedback? No, because we still have also G1 and we still have here the summing junction. Is J3 with H2 represent a feedback? Also no, it's not a feedback because we still have here backup point, we still have here another transfer function which is J2. So in this case, we know why we need to do some moving for for summing junction or backup point that we learned before in the table that we list before for reduction techniques. So the first step here, in order to simplify our system, we need to move this summing junction from the output to become ahead of G1. So instead of behind, become ahead, so become before G1. So we move this summing junction to here. And in this case, when we move J1, summing junction, we need to consider the impact of G1 of moving of H2. So instead of here at this point, we have only H2. But if I move it to before G1, if I move the value of H here to the place of G1 here, so the value of G1 will be multiplied by H, So what should I do? I need to divide H2 over J. We will see later on, okay? The second thing here, after we move this summing junction, now we have G1 and G2 will be in series or in cascade. So I can combine these two, G1 and G2. As we can see here, this is the first step. I move the value or the summing junction from this place to be at that place. Now I divide H2 over G1. In the original one, we have only H2, but here we have H2 over G1. Why? Because we move it before G1, so we need to consider the impact of G1 on the new input signal. Now G1, G2 become in cascade and it can be easily combined. When G1 and G2 are cascade, now we have H1 is the feedback for this G1, G2. Now we have G1, G2 is the new single transfer function for these two blocks, and it has one feedback which is H1. So the total G1, G2, H1, or we can say these blocks, these three blocks represent a feedback system, and it is a positive feedback. Positive feedback because of this positive value. So the new transfer function or equivalent transfer function will be G1 G2 over 1 minus H1 times G1 G2. As we can see here, it is G1 G2 over 1 minus G1 G2 H1. So this is the block diagram. The new feedback system, equivalent transfer function of the feedback. And this new transfer function now is in series with or in cascade with the value of G3. So now this can be combined, these two can be combined in cascade. So the new transfer function will be J1, J2, J3 over 1 minus J1, J2, H1. Okay. Both of these, the new combination of cascade G1, G2, G3 over 1 minus G1, G2, G3 will have this H2 over G1 as a feedback. Since it's taken from the output, go to the input, so it is a feedback system. So I can simplify these three blocks into a single feedback, which is a negative feedback system. So here we have a negative feedback. The transfer function is J1, J2, J3 over 1 minus J1, J2, H1, and the feedback value is H2 over J1. So the new combination of this function will be J1, J2, J3 over 1 minus J1, J2, H1 plus J2, J3, H2. Now this system is simplified, or this feedback system is simplified into this symbol or single transfer function, but we still have this the original feedback. And this original feedback, actually we call it unity feedback, because there is no H here, there is no H value here, so we call it unity feedback. So the value of HS in this case will be 1. So we have the original transfer function, which is Gs, is J1, J2, J3 over 1 minus J1, J2, H1 plus J2, J3, H2. The value of Hs is equal to 1. So in this case, the formula will become Gs over 1 plus Gs, because Hs is equal to 1. So it will be like Gs over 1 plus 1 times this Gs again. So this will be the value of the equivalent transfer function of our system. So as we can see here, how we simplify the complicated control system with multiple subsystems G1, G2, G3, multiple feedback H1, H2 into a single block with a single transfer function, which is J1, J2, J3 over this the value 1 minus J1, J2, H1, J2, J3, H2, and J1, J2, J3. This represents the equivalent transfer function with one input, which is RS, and one output, which is CS. I hope you understand this reduction method or reduction techniques. And as I mentioned before, these reduction techniques are used to simplify the complicated block diagram. And in the next part of this chapter, we will learn about the signal flow and how we can simplify the signal flow graph by using Mason's rule. Here there is one exercise. I need to find the equivalent transfer function for this complicated system, which consists of multiple blocks here with the value of transfer function already here defined, value s 1 over s and 1 over s, and the feedback also is s. So you need to find the equivalent transfer function or the closed loop transfer function of this system by using the reduction techniques. And here is the final or the answer for this exercise. I hope you try and practice to solve this exercise. More examples and more exercise are explained or are uh, explained in the slides. I hope you can refer to it. Thank you.